All right, welcome back. I just want to run through a quick example so that we can see this idea of taking a function's graph, looking at the signed area between that function's graph and the horizontal axis, and then approximating that amorphously shaped region with appropriate rectangles. And so for an example, let's look at the function f of x equals sine x. If you think about what this function looks like in terms of its shape, right, this ever oscillating up and down periodic function, well, the shapes here are actually quite amorphous in nature. And so, well, there's not some sort of geometric formula from high school geometry relating to the area of such amorphously shaped regions. And so we're in a case where we don't just have cookie cutter area regions. And now we're going to look on the x-axis between 0 and 3 pi over 2. So, conceptualizing this here, we could look at our interval between 0 and 3 pi over 2, and we want to use 3 rectangles and right endpoints to approximate. So first, if we want to divide into 3 rectangles, you sort of have to imagine this being broken into 3 pieces. Well, how wide is each piece? Well, the total width of our interval is just 3 pi over 2 minus 0, or 3 pi over 2, which means the width of each rectangle is just, well, there's 3 rectangles in total. It would be 3 pi over 2 divided by 3. And right, if you run the math on that, I suppose we've got a double-decker fraction here. You could, keep, change, flip, or multiply by the reciprocal, and you'd get 3 pi over 2 times 1/3. Actually, the 3's would cancel here, and then we'd end up with just pi over 2 as the width of each rectangle. And if you think about that, then, oh, that makes a lot of sense, right? Because to get from 0 to 3 pi over 2, if you go by pi over 2's, you'd get from 0 to pi over 2, then to 2 pi over 2. Technically, that would just be pi, and then to 3 pi over 2. But ultimately, here are our 3 rectangles. And without having a precise graph of the function, what we're ultimately going to do is build this first rectangle to be as tall as the function is tall, well, at the right endpoint. So the right endpoint here is pi over 2, and so maybe I'll write this here on the right so that it's a little bit easier to see. But the height of this first rectangle here is going to be f of pi over 2. The second rectangle that would show up, let me just throw this in here, the height of that rectangle would be f of 2 pi over 2. And then so on for all 3 rectangles. So when we look at the approximate signed area, sort of taking a nod from what we had seen previously, the approximate area, in this case, would be just the sum of the area of 3 rectangles, because we only have 3 rectangles in our picture. And in fact, each of those rectangles has a width of pi over 2. What about the heights? Well, the heights are dictated by the evaluation of the right endpoints. So here we'd have f of pi over 2, because that's the first right endpoint. Then we'd have f of 2 pi over 2. That's the second right endpoint. And then we'd have f of 3 pi over 2, because that is the evaluation of our function at the third right endpoint. So these are our 3 heights of our rectangles. So, well, to compute the function sine x, maybe it would help to see a unit circle just to remind ourselves of the nature of this computation. And we're going out to 3 pi over 2, which is down here at the bottom of the unit circle. We need pi over 2, which is up at the point, 0, 1. And then over here, we've got minus 1, 0. And then here, we've got, 0, minus 1. And every point on the unit circle is of the form cos theta comma sine theta. So in our case, we're looking for the sine values, which are the y coordinates. And so piecing this together here, f of pi over 2 would be sine of pi over 2, which is 1. And so ultimately our function height for our first rectangle is 1. Our function height for our second rectangle, 2 pi over 2, remember, is just pi. And so now we're over here at the point pi. The sine coordinate is 0. And so this is pi over 2 times 0. It's okay for a rectangle to have a height of 0. That's perfectly acceptable. If the function has a height of 0 at that point, then, well, approximating the function with a rectangle of height 0 would make perfect sense. What about here at 3 pi over 2? Well, down at 3 pi over 2, the function's height is minus 1. And we, in fact, want to use minus 1. I realize saying the word height and minus 1 in the same sentence may seem like a little bit paradoxical, but remember, we're talking about a signed area where area beneath the horizontal axis is accounted for negatively, and so if the function is evaluating negatively, we want to accommodate for that appropriately. So piecing this all together, we get what, pi over 2 times 1, which is pi over 2, we get pi over 2 times 0, which is 0, and then pi over 2 times minus 1, which is minus pi over 2. Add it all together, and we get 0, which, well, this seems like a whole lot of work for nothing, but that nothing is actually meaningful here, right? Because when we are approximating the signed area between this function's graph and the horizontal axis, incidentally, we had rectangles above the horizontal axis with exactly as much area as rectangles below. And so this specific example is very much like, if you recall a couple videos ago, the analogy of walking to class and then walking back from class, where you were walking to class and then you were in class, and then you were walking back from class, and ultimately over the course of time, your net change in position was 0, which is effectively what something like this is capturing. Now, I will say, what we have done here in this example is only approximate, right? Because the sine function is this sort of like curvaceous periodic function, and these rectangles are not curvaceous. They are well, they are rectangular. So we are just getting an estimate, but we're getting a pretty good idea of the nature of the sine function. And, well, as we know the sine function sort of undulates up and down, it's not altogether surprising that we would get area above and area below that could be canceling out. So, yeah, I just wanted to hammer through a specific example so that we could see this in action. We could see an interval of a particular width divided into a certain number of sub-intervals, each sub-interval a width of a given rectangle, and then evaluating the function of interest to determine how tall each of the rectangles are whenever we are considering our approximate area. But we will see in time just how potent this idea of approximating regions under functions graphs by rectangles will be. But for now, hey, at least we've hammered through one example so that we have this under our belt before we proceed into other things.